All right, so last time we looked at a process called integration, which was for finding the antiderivative. So that is for when you know the derivative and you want to go backwards and find what the original function was. Okay, but before we do that, I want us to review chain rule. It was a little shaky for some of us on the last test especially. But remember, chain rule is for doing functions that are kind of within other functions, like f of g of x. Okay, and so remember the format for that was derivative of the outside times derivative of the inside. So if we're labeling that, remember that was always kind of what we looked at. So this is for what we would consider more complicated functions, right? Where maybe it's not just plain old x raised to a number, or maybe it's not just e to the x power, it's e to a more complicated power. Any of those types of things we use chain rule for. All right, so we can use substitution, and the name of this method implies what we'll be doing. We'll be substituting values in for other values. So we use substitution when there are two functions and when one is the derivative of the other or close to it. So it certainly doesn't work for all functions, but there's a big group of functions that this is going to work for. The point of this method, the point of any sort of substitution, even back when we did it in algebra, the point of substitution is to make the problem easier to solve. So the point of this method is to allow you to find the antiderivative of a simpler function rather than the more complicated one that you're looking at. So if you can try to remember that, the point of this method is always to do the calculus on a simpler function so that we don't have to strain our brains as much. Alright, so before we jump into using this method, the steps for integration by substitution, and you may need to pause this video multiple times throughout this lesson just to make sure that you understand what's going on. So the first thing is you're going to let u equal the letter u equal g of x or the inside function. In other words, if you can pick out the inside function, you're going to replace it with a single variable, and we're going to use what we call u. This method is also called u substitution in other textbooks. So then you're going to find the derivative of u. du means the derivative of u. In other words, you're going to find the derivative of that g of x function. So here's the most important step in the whole method. This is why it's called substitution. So the third step is you're going to use substitution to convert the original problem into a simpler one involving u, the letter u. Here's a disclaimer. You want to make sure you adjust the constant as necessary. We're going to get to many examples like this, so for now let's just write down the steps. Step number 4, now that you've made the equation simpler, now you're going to evaluate the simpler integral. And then lastly, once you're done kind of doing the simpler operation, then you're going to plug what I would call the uglier part back in. In other words, you don't get to get rid of the ugly part altogether. You just get to do the complicated calculus part on a simpler function, and then in the end you have to replace it back with what you started with. Alright, so let's just kind of take this slow again. Anytime throughout today's lesson if you need to pause, then that's what you need to do. So what if I told you I wanted you to find the antiderivative, not derivative, right? We already know the derivative. This is the derivative already, okay? So what you're going to do is, over off to the side, you're going to let the letter u equal the complicated part of this function, or the inside part of this function. Sometimes that'll be in parentheses and will be relatively easy to find. So the derivative of, or sorry, the inside function is 4x plus 3. Okay, and then you're going to find the derivative of that. So don't look over here. We're going to find the derivative of u. Now this is where it gets a little tricky. The derivative of this is 4, but then we also have to say dx because it's notation because we're changing from u to x. Okay, so just like there's notation here, we need notation here as well. All right, so your job is to, we're going to rewrite this. You don't have to do this every time. Once you get the hang of it, you won't have to. I'm going to rewrite this like this. Notice all I did was move the 4 kind of in the back. So notice I can replace each part with something involving u, right? I can replace this parentheses to the 4th power with just u to the 4th. Okay, and then notice the 4 dx is exactly what du was. So in other words, I'm going to, rather than try to do this mess, I'm going to do the antiderivative of u to the 4th du. So notice we always have two components, something involving u and then the du. Okay, so ignore this ugly mess for a minute. Let's just take the derivative of this. We know how to do that, right? We bump the power up by 1 and we multiply by 1 over that new power. So instead of 4, now our power is 5, and don't forget your plus c. But then in the end, we weren't really using u to begin with, right? We were using 4x plus 3. So in the end, in place of u, we plug the 4x plus 3 back in. Okay, but notice the calculus portion, which is this line that I'm pointing at, we did on a simpler function. All right, so it'll be good for us. We won't do this on every one, but let's check this. If we take the derivative of what we think is the answer, we should get back what we started with originally. It's just we're going to have to use chain rule, so think about that. Okay, so if you take the derivative, the 1/5 is going to pull over. Now we're doing derivative, right? We're checking to see did we do the antiderivative right. So if you move the power to the front, and you would, right, you're going to get 4x plus 3 to the 4th power. But then you're going to have to do chain rule times 4. Okay, in other words, chain rule is derivative of the outside and then times derivative of the inside. And then notice a 5th times 5 goes away, right? And we end up with 4 times 4x plus 3 to the 4th. Notice that is precisely what we started with, right? Okay, notice that's exactly what we started with here, right? So antiderivative is simply going backwards. It's where we know what the derivative is and we're trying to figure out what the original must have been. Okay, so you can always check, remember, the antiderivative by taking the derivative of it, and you should get back the original again. Or what you started with anyway. Alright, so let's see if we can figure out how to do one like this. So x cubed minus 2x parentheses squared, and then times 3x squared minus 2 dx. Now, just for a minute, imagine what a nightmare this would be to FOIL out and then multiply using distributive property. It would be a mess, okay? So instead, we're going to substitute something and make the problem simpler, okay? So which one are we going to pick as our quote inside function? Notice we have two things in parentheses. Well, we'll want to pick the one that has the higher power because our goal is to have something for u and then have something where the derivative is represented also. Okay, so don't look over here, but let's talk about what the derivative would be. What would the derivative of this be? It would be 3x squared minus 2, but then we always ended in this. Okay, this is just notation. This is just because we're switching from u's to, or x's to u's, and we need to indicate that. So if you look back over here, notice how perfect this is. This is exactly what we got for du. Okay, and this, rather than saying parentheses squared, right, that ugly parentheses, I can replace that ugly parentheses with u, so this would just be u squared. And notice how much nicer of an antiderivative that is. Look how much shorter and more pleasant that is than this monster. Okay, so I can much easier take the derivative of this, so how would I do it? Well, bump the power up by 1 and multiply by 1 over the new power. Don't forget your plus c. And then in the end, you just stick the ugly part back in. So what was u all along? It was x cubed minus 2x cubed plus c. Okay, so notice the process, right? This looks similar to this. We just took u out and replaced it back with what u was. Okay. So we're going to practice some of these. I promise if you'll practice these, you will get a better hang of it, but there's really no substitute for practicing. Just watching me do these videos is not going to be enough. You're going to need to kind of practice them as you go. Pause the video as you go, all that good stuff. All right, anytime you have a fraction written like this, maybe it would be best if you would kind of pull them apart into separate pieces. In other words, we have two distinct parts of this function, so we're just going to really highlight that by pulling apart the fraction into two pieces. Okay, so what would we likely make our u? We would make our u the complicated inside portion, right? So 2x squared plus 3. Okay, so ignore what we have over here. What would the derivative of this be? So it would be 4x, and then don't forget this dx notation. Okay, always make sure to remember that. All right, so let's see what we have. Notice we have du here, right? That's exactly what du is. And then notice what this would be. It'd be 1 over u cubed, but another way to write that would be u to the negative third. So if I want to solve a simpler integral, and I do, I can just integrate u to the negative third du. Okay, notice there's always two components. There's a u to some power, and then there's a du. Okay, so now let's do the antiderivative. So be careful with negative numbers, right? When you add 1 to the power, you're going to get like a negative number that seems smaller, right? So it's going to be 1 over the new power, and then u to the 1 more power, and then don't forget your plus c. And then lastly, just always make sure that you plug in what the ugly part was originally. And then just like before, remember, I don't want to see negative exponents, so this would actually be the answer that I would be looking for. This right here. Okay. By the way, if you wanted to, we won't, but if you wanted to, you could take the derivative of this and you would definitely get this back again. Okay, if you knew what you were doing as far as derivative goes. All right, so let's do one more, and then we're going to look at some that may not be as perfectly set up as these have been. Notice we've always been really lucky to have the original u show up and then also the du show up somewhere in the problem. So my first suggestion would be to rewrite this. This is 3t squared, right? And this would be t cubed plus 2 to the 1/2 power. Okay, notice we end with that notation because we are talking about the letter t. So we're going to let u be the inside function. So u is going to be 2 cubed plus 2, t cubed plus 2. And the derivative of that would be move the power to the front, 3t squared, and then dt. Okay, one more time, just notation, right? So if you want to, you can kind of move this around, right? But notice this right here would be u to the 1/2 power. And then this right here together would be du. So if you like that better when we rewrite it, then rewrite it. Move the 3t over there. Okay? But essentially this is what we really have. The antiderivative of u to the 1/2 du. And again, the point of substitution is look how much nicer that is than that. Okay, so be careful with fractions. When we add 1 to the power, we're going to get 3 halves, right? So it's 1 over the new power, and then u raised to that new power. So remember, that's going to flip this, right? So this is just going to be 2/3, and then we're going to replace u with the original, which was t cubed plus 2 to the 3 halves plus c. Okay, so we haven't done this in a while, so let's just check it real quick. Okay, if I take the derivative of this guy, then I should get back what I started with. Okay, I'm just going to have to use chain rule. Remember, this is like the backwards version of chain rule. Okay, so what are we going to do with the constant? Well, we pull that over. And then what do we do with this power? We bring it to the front. We leave the inside the same. And we reduce the power by 1. Okay, but then we also have to multiply by the derivative of the inside, which in this case would be 3t squared. Okay, notice that goes away, right? 2/3 times 3 halves is just 1. And then notice you get the very thing you started with, right? So 3t squared and then times t cubed plus 2 to the 1/2. Okay, so we can put a check mark there, right? That's exactly what we started off with, minus the square root, right? Just because we wrote it differently. All right, so now let's look at some where we might need to make a constant adjustment. Notice that was in the steps, right? I said be careful to adjust the constant if necessary. So let's look at some where that might be necessary. So what if I told you to integrate 12x times 3x squared plus 4 parentheses cubed dx? So first thing is, maybe we'll rewrite this. We could rewrite this as 3x squared plus 4 cubed and then times 12x dx. If you like it that way better so that the pieces are kind of separated out, then you can do it that way. So what would I likely make my u? Remember, you make the u the inside function. So the inside function is clearly 3x squared plus 4. So if I find the derivative of that, I get 6x dx. Okay, that's just notation. But notice I don't have a perfect scenario here, right? I do here. This is just u cubed. But here I don't quite have what I want, right? Notice I have 6x here and I want it to be 12x. Okay, so I wanted 12x here dx, right? So that it matches up with this. Okay, so notice what would I need to do to make that happen? So you just need to be careful. If all you say is du, then you're really putting in 6x dx instead of 12x dx. So what could you multiply 6 by so that you would get the 12 that you would like to have? Well, you could just multiply by 2, right? So let's practice that. What is 2 times the 6x? It would be 12x, just like we would like to have. So now when we rewrite this, this is really the same as the derivative of 2u cubed du. Notice I'm just using what I wrote in green here. And now let's do the antiderivative. Pull the 2 over, bump the power up by 1, multiply by 1 over the new power. Don't forget your plus c. And in the end, clean up anything you can. 2 times a fourth would be a half. And then always, always replace the u back with the complicated part that it started out being. Okay, it will always just be a number that you need to multiply by to make it work. So let's try a few more of those. So 2x over 3x squared minus 1 dx. Okay, so we tried one like this before, and remember I said it might be better if you split it up this way. In other words, pull the pieces apart so that it makes it easier to discuss or think about. All right, so over off to the side, you always decide what you're going to make u. So we're going to make u the bottom function, 3x squared minus 1. So don't pay attention to this. You actually just need to do the derivative of this. Okay, so du is going to be 6x, and then don't forget your notation of dx. So notice this is okay. This is just 1 over u. Okay, you do need to remember that this is our special case, right? This is the power rule doesn't work for 1 over u to the first power. But notice this is not quite right. Right? So if I plug u du in, I'm going to get 6 when I'd rather only have 2x. So right here I wanted this to be 2x dx. So how can I make a 6 be a 2? Okay, notice this is a bigger number than the one I want. Okay, so I'm actually going to need to multiply by a fraction or divide. Okay, so think about this. 1/3 du would work, right? Think about that. 1/3 times 6 would be 2, so that works out. You always want to ask yourself, does this work out or not? So in the end, we're finding the antiderivative of this. Okay, so don't let the 1/3 throw you off. It's just a constant. Pull it over. And then remember, this is our special case, right? So the antiderivative of 1 over u is the natural log of u. Don't forget your absolute value bars plus c. So in the end, it's going to be 1/3 ln of 3x squared minus 1. Those are absolute value bars plus c. Your final step is always to just replace that function back where you substituted. Okay, so if you wanted to, again, find the derivative of this and you will get this back again. All right, so let's do one more just straightforward problem, and then we'll look at maybe some word problems that ask us to do some of these things. So x times e to the negative x squared dx. So the first thing I'm going to do is, just like I did for the fractions, I'm going to rewrite them kind of as separate pieces. I know e is its own thing, so I'm going to definitely make it its own thing. Okay, and then I'm just going to move the x over here. So you want u to always be the inside piece. Okay, so the inside piece of an e function is always the exponent. So the derivative is going to be negative 2x and then dx. So notice, I've got part of what I want, right? How would I rewrite e to that complicated power? Well, instead of writing the complicated power, I'm going to write e to the u. But notice this doesn't perfectly match up, right? This is not what I get here. So what did I want this to be? I wanted this to be 1x dx. In other words, I did not want the negative 2 there. Okay, so how can I get rid of an unwanted number? I can just multiply by 1 over that number. So think about that for a minute. If you do negative 1/2 times negative 2, you're going to get 1, and that's exactly what we want, correct? So the rewrite step looks like this. It's going to be negative 1/2 e to the u du. And now, rather than having that complicated e function, I'm dealing with just plain old e to the u. So we pull the constant over, right? The antiderivative of e, remember it's the special case, always itself, right, plus c. And so last but not least, now stick the negative part back in, or the ugly part. Okay, notice if you took the derivative of this, it would be itself times the derivative of the exponent, and you would get this back again. Or this back again, sorry. Alright, so before you work on the word problems, honestly, you need to maybe rewind the video, watch it again, okay, because these concepts are important, and frankly, they're not going away, so you can't just avoid them and think, oh, I'm just going to ignore this lesson because I don't like it. Okay, that's really not how it works. So just know that we're going to build on this. So like the next lecture or two might really look at this a little further, so you definitely want to make sure that you process it. Alright, so let's look at a couple of example problems, application problems. So I'll try to keep these not so wordy. But the marginal price for the weekly demand of X bottles of shampoo is P prime of X equals negative 6,000 over 3x plus 50 in parentheses squared. So notice I'm giving you the derivative, right? And what I'm going to ask you to find is the original. In other words, the regular old p of x, not p prime. So find the price demand function. If the weekly demand is 150 when the price is 8. And then lastly, once you get that equation, I want you to tell me what is the demand when the price is $6.50. So if I want regular old p of x and I have the derivative, I need to take the antiderivative so that I can get back to regular old p of x. Okay, so it's important that you know how to say that, right? I don't want the derivative equation. I want the original equation. All right, so over off to the side, we have to, because this problem's more complicated, we have to use some sort of method, okay, and we're going to use substitution. So what is the inside portion of this problem? Notice the inside would be 3x plus 50. So the derivative of that would just be 3 dx. Okay, notice I'm just underlining the notation every time. And notice that is not exactly what I have here, right? So let's rewrite this. Let's rewrite this like I've recommended that you do. Pull the fraction apart into two pieces so that you can really kind of clearly think of it like two separate pieces. Okay, so I think I can do this part just fine. Okay, this would just be u to the negative 2 power, right? So in place of this ugly thing, I'm going to replace it with u. But I cannot say this is du. It's definitely not, right? Du is only 3, and I need it to be negative 6,000. So think about that. What could you multiply 3 by that would give you negative 6,000? Well, negative 2,000 would work, right? And then notice, negative 2,000 times the 3 would be perfectly negative 6,000. So the point of this was we would much rather find the antiderivative of this than the ugly fraction that we started with. Okay, so who cares that that number is large? When you have a constant, you just pull it over. And then we're going to bump up the power by 1. Okay, so think about that. What happens when you add 1 to negative 1/2? You're going to get 1 over negative 1, and then u to the negative 1. Okay, don't ever forget your plus c. So if we clean this up a little bit, we're going to get 2,000, right? Because this times this would be a positive 2,000. And then we're going to write this on the bottom because it is a negative exponent. So it's just going to be 2,000 over the 3x plus 50 plus c. But we kind of did problems like this last time. Now we just need to find c. In other words, for these application problems, we don't leave the constant as c, we actually figure out what it is. Okay, so here's what we have so far. We know p of x looks like 2,000 over 3x plus 50. We just don't know about this plus c thing. Okay, but if you read the problem, we do know that when we demand 150 items, that the cost is specifically $8. So when we plug in 150 in for x, and we add this unknown constant, we're supposed to get 8. So just let your calculator do all of this. Okay, it comes out to be something pretty nice. It's 4. Okay, and notice if you subtract 4 from both sides that c is 4, because 4 plus 4 is 8. So here's my final answer for p of x then. It's 2,000 over the 3x plus 50, but now that I know c, I insert what c is. Okay, so that's part of what I asked you for. And then the second question says, what is the demand when the price is $6.50? Okay, so now they're asking you to use this equation. So if 650 is the price, then what must the x have been? That's what they're asking. So this is just a little bit of algebra. Okay, so if we subtract 4 from both sides, we're going to get 250, right, equals 2,000 over 3x plus 50. So if you think of this as over 1, then hopefully you'll see that we really should just cross multiply here. Anytime you have a fraction equal to another fraction, you just cross multiply. So you're going to do $2.50 times that 3x plus 50. So 250 times 3x plus 50. And you're going to set that equal to 1 times 2,000. So do distributive property and you'll get 750x plus 250 times 50 is 125 equals 2,000. So subtract 125 from both sides and you'll get 750x equals 1875. And then last but not least, just divide by $7.50. Or 7.5 rather. So in the end, you're going to get 250 units. All right, one more application problem, and then I'm going to let you go practice on your own. By the way, I want to see who's watching the videos and who isn't. So for kind of an extra assignment this week, I want you to email me the answer to example 8, okay? And honestly, I wouldn't tell your classmates this, okay? This is kind of a free 100 for you, but it's kind of less helpful to you if you inform everybody, okay? So kind of keep that in mind. So I want you to email to my email address that's on the syllabus. I want you to email me the answer that we just got for example 8, okay? Just curious to see who's watching the videos and who isn't. All right, but let's do the last example. The weekly marginal cost from the sale of X athletic shoes is C prime of X equals 12 plus 500 over X plus 1. Where C of X is in dollars. So in other words, I'm telling you what the marginal cost is. I'm asking you to go back and tell me what the original cost function, just plain old C of X, was. So if the fixed costs are $2,000, then I want you to find C of X. And then last, just to make sure we remember what the difference is, what if I ask you what the average cost per pair of shoes if 1,000 pairs are made? By the way, this is X pairs here also. So what is the average cost per pair of shoes if 1,000 pairs are made? So I'm not trying to trick you. I'm not asking you exactly how many shoes. I'm asking you for how they're sold, right? Which is pairs of shoes. So if I want to find the original cost function, I'm going to need to do the antiderivative of 12 plus 500 over X plus 1 dx. Alright, so I'm going to simplify this. So this is the antiderivative of, I'm going to pull these apart into separate pieces. 12 dx plus the integral of 500 over x plus 1 dx. In other words, I don't need to make this more complicated than it is. We'll talk about that in a minute, but this one is a little more challenging, right? Alright, so for this piece only, we're going to use substitution, right? We're going to let u equal x plus 1, right, the complicated piece. And so the derivative is going to be just 1 dx. So let's think about what I have. I'm going to leave this alone for a minute. I'm just not going to work that out. I'm just going to focus my attention on this one. So notice what I have, right? I have the integral of 1 over u, right? That takes care of this. But if I just say du, it's only going to include a 1 and it needs to be 500, right? So this is actually times 500 du. Okay, so I didn't do quite as much work there as I have in previous problems, but remember, you separate these out, at least in your mind. Okay, so notice this one's du and this one's dx. Okay, so try not to let that throw you off. It's not going to be as bad as you might think. So I'm just going to keep carrying this down. I'll deal with it at the end. But as far as finding the antiderivative of this, I would move the constant, right? And then this is my special case. The antiderivative of 1 over u is just the natural log of u. And then plus c. But then notice I can substitute this, so I think it's time we can go ahead and figure this out. The antiderivative of 12 is just 12x. Like, what function would give you a derivative of 12? It would be 12x. Okay? And then here we're going to replace the u with what it originally was, which was x plus 1. So we have our cost function, but right now we have this pesky c, right? So now we need to find c. So it said the fixed costs were $2,000. That means that when we sell 0 items, our cost is still $2,000. So if I plug in 0 everywhere there's an x, and I'll want to use my calculator, right? But the natural log of 0 is just 0. Okay, and then plus c, that's supposed to be 2,000. So this just becomes 0. So 0 plus c is 2,000. So obviously c is just 2,000, right? So c is not always the number that you're just given right off the bat, but in this case everything else went to 0, so it actually was. Okay, so c of x is going to be the original function I got, which was 12x plus 500 times the natural log of x plus 1, absolute value of that, and then plus the fixed cost of 2,000. Okay. By the way, not to be obnoxious, but if you found the derivative, what's the derivative of 12x? It's 12, right? What's the derivative of this? Well, the 500 would pull over the derivative of the natural log of something is 1 over that something, and then times the derivative of the inside, and you would get 500, well, let me move that back down. You'd get literally this again. So 500 times 1 over that. All right, so that's the cost function, but then notice it asks you for average cost. So just make sure you read the problem carefully. In other words, it's not asking you for c of x and plug in 1,000. It's asking you for the average cost. And remember, average cost is total cost divided by items sold. So in the end, c bar of 1,000 is going to be this c function with 1,000 plugged in. So 12 times 1,000 plus 500 times natural log of 1,000, one more 0, plus 1 plus 2,000, and then over 1,000. Okay, and notice this is average cost per unit, so you're just going to round this to the nearest penny. But if you work this all out on your calculator, you should get $17.45. So I know the antiderivatives are something new for you, but again, they're not really going away. And remember what I said in the last lecture. The better you understand derivatives, certainly the easier antiderivatives are to understand.